Hello all, Dr. Caudell here. We are starting on chapter 6 now. So in chapter 6, this is thermochemistry. The first topic in chapter 6 is using conservation of energy, so sort of similar to conservation of mass that we've heard of before, to predict the qualitative exchange of kinetic and potential energy. So let's go into some different forms of energy. So to define this first, energy is the capacity to do work. From the name of this chapter, thermochemistry, you may assume that we're dealing with thermal forms of energy, and you would definitely be correct. So thermal energy is the energy associated with the random motion of atoms and molecules. So we built up, we're familiar with atoms now and molecules, how molecules are composed of atoms. So molecules composed of atoms, how they move about the motion of these atoms and molecules is what we call thermal energy. Radiant energy comes from the sun and it's Earth's primary energy source. We also have chemical energy, the energy stored within the bonds of chemical substances. So these are certainly interrelated as far as we're concerned in chapter 6. So within the bonds of chemical substances, if we think about a water molecule, and we'll get into drawing molecules just in a little bit later on in the semester. So this is an example of a bond between hydrogen and oxygen, and then there are two of these bonds that make up water. There's energy stored within these bonds in what we call chemical energy. That energy will change whether these bonds are breaking or being formed. Right, so when a hydrogen atom comes together with an oxygen atom, that is a bond being formed. These bonds can also break. Depending on the molecule, there's more likelihood of these bonds breaking or being formed, just depending on these atoms and the environment that that molecule or those atoms are in. So some molecules break apart more easily than others. We also have nuclear energy, so the energy stored within the collection of neutrons and protons in the atom. If you go on to take general chemistry 2, which I hope some of you do, this nuclear energy would get to more in general chemistry 2. So now we know neutrons and protons. The idea of the atomic bomb also has to do with nuclear energy. So how we can actually change the number of neutrons and protons within the nucleus of an atom. Then within this first topic, we're dealing with potential energy versus kinetic energy. So potential energy is the energy available by virtue of an object's position. So we have potential energy if some box is higher up and then it may fall down this hill. The height that that box is at has to do with its potential energy. Then if that box were to actually fall down the hill or roll down the hill, that energy in motion is the kinetic energy. So potential energy by the virtue of an object's position, the kinetic energy is the energy in motion for an object. So here in this practice problem, a bicyclist is stopped at the entrance to a valley as sketched below. Then from this picture and from these different letters here that are marking different positions, we're going to answer these questions. So highest potential energy, lowest potential energy, kinetic energy, speed, and a little bit to do with friction as well. So some physics concepts in this topic for sure. So we should add kinetic energy to this list technically. So kinetic and potential energy, we're gonna go more into. So kinetic energy is energy in the form of motion. And that kinetic energy is proportional to the mass of what's moving and the square of the speed of the motion. So we saw this equation just very briefly in the gases chapter in chapter 5, where kinetic energy is equal to 1/2 mv squared, where m is the mass and v is the velocity. You won't really need to worry about plugging in numbers to this equation, just be familiar with the connection between kinetic energy being based on the mass of the object and the velocity. So for our practice problem, this means the bicyclist has kinetic energy whenever she's moving, right? So when she's in motion, and that the faster she moves, the more kinetic energy she has. So as this velocity term increases, the more kinetic energy she has. If kinetic energy is energy in the form of motion, then the more motion there is, then the more kinetic energy there is. Next, we're going to use the fact that potential energy is the energy from the potential action of a force, and that potential energy is proportional to the strength of the force and to the distance over which it can act. You also won't need to plug in values to solve for potential energy, just be familiar with what goes into what decides how much potential energy there is. So potential energy is proportional to the strength of the force. Mostly we think of this as being the gravitational force, and to the distance over which it can act, or the height. So going back here, this potential energy of this box, if the box was up a little bit higher, then there's more potential energy, right? So the distance over which that force can act is higher if this height here is higher. So the greater the height here, the more potential energy. So as mentioned, that force is the gravity pulling the bicyclist down, and the distance over which it can act is her height above the bottom of the valley. Once she reaches the bottom of the valley, gravity can't pull her any further down, right? She's against the surface of the valley. So when she's all the way this direction, then she can't be pulled down any further by gravity. So also based on what we talked about, that means the bicyclist's potential energy will be higher the higher she is above the valley floor. So the most potential energy when she's first starting out, so this distance is greater. As this distance gets smaller, then her potential energy is going to get smaller. We can see that visually. We can also see that with this equation for potential energy. As this height term gets smaller, potential energy gets smaller. The higher this height term, the greater this height term, the larger the potential energy. The third important point here about energy, so that principle of conservation of energy, just as mass could not be created nor destroyed when we are balancing chemical equations, we also have this principle of conservation of energy, which tells us that energy can neither be created nor destroyed as well. So energy can neither be created nor destroyed, so we keep that in mind. It's just transferred between objects. So this means that as the bicyclist loses potential energy as she's going downhill, right, that height is getting smaller, she must gain an equal amount of kinetic energy as she is speeding up. So her potential energy is decreasing as she's going down the hill, but her speed is increasing. So as her potential energy is going down, her kinetic energy is going to be increasing. So this potential energy has to go somewhere. It's converted into kinetic energy. In that way, we are abiding by the principle of conservation of energy, and very importantly, the total energy has to remain constant. If kinetic energy is going up, that means potential energy is going down. This principle is going to be really important as we get into applying these different energy concepts to chemistry. If one solution is losing energy, then another solution or another object has to be gaining that energy. So energy has to stay constant. Then in the same respect, when the bicyclist gains potential energy by coasting back up, then she must lose kinetic energy as she's slowing down. And just to remind you again, here we have height that is directly proportional to potential energy. And then for kinetic energy, this is a velocity term here. So that velocity term is also directly proportional to kinetic energy. As velocity is increasing, kinetic energy is going to be increasing. Then as height is decreasing, potential energy would be decreasing, and vice versa. So let's apply this reasoning to our problem and pick out what different points in the valley match up with the different problems. Since her potential energy is proportional to the height above the bottom of the valley, the bicyclist would have the highest potential energy at F and the lowest at D. So lowest at D makes sense. It's the lowest height she'll be at throughout this bike ride. Then A is where she starts. If she ends up at F, this is going to be the highest potential energy because of this height difference. That's a larger height than this height difference. All right, so H2 is greater than H1, meaning that the highest potential energy would be at point F, lowest at point D. So highest at point F, lowest at point D. Let's go on to the next questions now. So we know kinetic energy is proportional to velocity. We're just focused on velocity here and not mass because her mass is not changing throughout the bike ride. So she's a constant mass object, right? Her mass is not changing. So only velocity is changing here. Then that change in velocity will lead to a change in the kinetic energy. And using this relationship, when potential energy is its lowest, kinetic energy is the highest, and vice versa. When potential energy is at its highest, kinetic energy would be at its lowest. So since kinetic energy increases as her potential energy decreases, the bicyclist would have the highest kinetic energy exactly where the lowest potential energy point is. So the highest kinetic energy would be at point D. She's gained all this velocity as going down the hill. So highest kinetic energy at point D. Next, the highest speed point. Well, that goes back to our formula for kinetic energy. When kinetic energy is at its greatest, then the velocity or the speed also has to be at its greatest. As a reminder from physics, the speed of an object is how much it's moving over a period of time. To call this a velocity term just means it has a directionality to it. So the bicyclist is moving some direction, but still reported in a unit of length over time. So units might be feet per second or meters per second. So velocity and speed have the same units. Velocity, though, includes a directionality component. So some distance over time, but velocity with a directionality component. So when kinetic energy is at its highest, then the speed and the velocity will also be at its highest. So kinetic energy is greatest here. That means her speed will also be greatest at point D. So highest kinetic energy at point D, the highest speed and the highest velocity too at point D. So now kinetic energy at D versus B, potential energy at D versus B. So we're comparing D versus B here. So for kinetic energy, we know it's greatest at point D. At point B, what's happening? Well, she's losing some of her potential energy. It's being converted into speed, into kinetic energy. So at point B, she'll have some speed and some amount of kinetic energy, but at point D, it'll be even higher because she's traveled this distance plus this distance. So more potential energy at point B, but more kinetic energy at point D. Next, we'll answer, would the bicyclist's total energy be higher at point D or point B? And suppose the bicyclist lets off the brakes and coasts down into the valley without pedaling. Even if there was no friction or air resistance to slow her down, what is the farthest point she'll be able to get to without pedaling? So when she's starting out, she's not moving, she has zero kinetic energy. That means her total energy is just equal to her potential energy. She has zero kinetic energy at that point. As she starts her ride, that potential energy is converted into kinetic energy because we remember that energy cannot be created nor destroyed, so it gets converted into a different form. For the bicyclist to be able to coast up the other side of the valley to a point higher than the valley entrance, for example, to point F, she'd have to have potential energy higher than her total energy, which is impossible. So she has total energy, which is equal to her kinetic energy plus her potential energy. Because she started out at this point, the energy she has to work with is this potential energy due to her placement at height from position A. So her potential energy is converted into kinetic energy, then at this point, her kinetic energy is then converted back into potential energy. So her velocity will slow down as she's going back uphill, and she'll regain that potential energy. Because she started out at this height, that determines her starting potential energy and her start total energy. Her total energy is starting out at this height. That means the only energy she has is the potential energy based on this height at position A. That means if she were to use all the energy she starts with, then she can only reach an equivalent point on this side of the hill. Because of the conservation of energy, she doesn't have the energy here to make up to get to from point E to point F. So again, she's starting out at point A. That potential energy dictates her total energy because she's starting out with 0 kinetic energy. She's not moving. So the total energy she can get to on the other side of the hill is still based on the height from her starting potential energy. This height then has to be the same as this height over here. So even if she loses no energy due to friction with the road or from air resistance, the bicyclist can go no higher than the valley's entrance without pedaling and inputting more energy. So only based on her starting amount of potential energy, that means she can get to that point E. Then is her energy higher at point D or point B? So here we're looking at B versus D, but we're no longer considering just potential energy or just kinetic energy. We are asked about the total amount of energy. The total amount of energy, whether it be in the form of potential energy or kinetic energy, is going to be the same for her throughout her bike ride if she doesn't pedal. So even though D is lower than B, that means her potential energy would be lower, but her kinetic energy would be higher at point D. And remember, her total energy equals the kinetic energy plus the potential energy. The total energy she has, whether it's in kinetic energy form or potential energy form, is going to be the same at both of those points. So total energy throughout the ride is the same at both points. Here is the completed final answer for this practice problem. Again, not really necessary to understand how to plug in values for these equations. Just understand that potential energy relates to the height of the object, and the kinetic energy relates to the velocity. Mass is also a factor in kinetic energy, as well as in potential energy and the force of gravity. And the other huge takeaway here is that the total energy is going to equal the kinetic energy plus the potential energy. And if the kinetic energy is transferred into the form of potential energy, we're still not creating nor destroying any energy. So regardless of the form, these are going to total up to the same amount of total energy. Next, we're going to go into some more background on energy, heat, and temperature now. So heat is the transfer of thermal energy. To remind you about thermal energy that we covered near the beginning, so thermal energy is the energy associated with the random motion of atoms and molecules. So the random motion of atoms and molecules, heat is the transfer of the thermal energy that's caused from the random motion of atoms and molecules. So we think of heat as a transfer of energy between two bodies or two objects that are at different temperatures. So temperature, in this sense, we define it as a measure of the amount of thermal energy. But to be clear, temperature is not the same as thermal energy, right? So temperature is how we measure the thermal energy, but thermal energy is due to the motion of atoms and molecules. So we measure the motion that leads to a change in thermal energy with this notion of temperature. But again, temperature does not equal to thermal energy. It's just how we measure the motion of those atoms and molecules. So heat is the transfer of thermal energy between two bodies at different temperatures. How much thermal energy is in a hot object versus a cold object? We describe that by the temperature, Then the hot object is going to transfer some of its thermal energy to the cold object if they are in contact. Heat is what is transferred between the hot object and the cold object. Next, we have the title of our chapter 6 here. So thermochemistry is the study of heat change in chemical reactions. So through a chemical reaction, this will create some thermal energy. Then heat is the transfer of thermal energy from that reaction, maybe into an aqueous solution. Let's say, for example, we had some reaction taking place in this test tube. It produced some heat. Some heat is going to transfer from the test tube into that aqueous or water that surrounds the test tube. So energy cannot be created nor destroyed, but chemical reactions can release heat or absorb heat based on the chemistry that's happening in the reaction. Are bonds being broken? Are bonds being formed? Is gas being released? What is happening at this molecular level? That's how we think of thermochemistry. So the study of heat change from chemical reactions. Then importantly, the system is the specific part of the universe that is of interest in the study. To somewhat simplify how we approach these sorts of problems, we can think of the universe as this box. We can think of the system here. Really importantly, whenever we talk about these energy transfers, it's always in reference to some defined system. Is the system a chemical reaction? What is the system? We need to define that in order to say, is heat being transferred into or out of the system? Remembering that energy cannot be created nor destroyed, and heat is a form of energy. So heat is a form of energy. Whatever is happening in reference to the system is going to relate to what's happening in these surroundings. To simplify what we're looking at, we think of these surroundings plus the system being our whole universe that we consider. So energy cannot be created nor destroyed. Heat is a form of energy. And we think about heat being transferred into or out of a specific system. So always in reference to some system that we have to define. Then here, these are the different types of systems. In an open system, both mass and energy can be exchanged. Notice here, this is completely open and we'll have some heat exchange from the surface of this vessel into these surroundings. In a closed system, we'll still have an exchange of energy. So we'll still have this exchange of energy because some heat can still be transferred from this thin glass vessel. So from the thin walls here, we'll still have some transfer of energy, maybe to or from this solution inside through the thin wall of this vessel. But we won't have any exchange of mass because of this stopper here. So in the open system, we have an exchange of mass because water vapor, so gaseous water, can still flow into and out of this vessel. That's why this is an open system where both mass and energy can be exchanged. So we think of this portion being how mass is exchanged, then this portion is how energy can be exchanged. Now, in a completely isolated system, which is pretty hard to obtain in a standard lab setting, but in an isolated system, we don't have an exchange of mass nor energy. So the stopper is on here and we put some insulated material so that no energy in the form of heat or in any other form can be exchanged to and from the solution that's in this vessel. So open versus closed versus isolated systems. So we covered thermochemistry and the importance of defining what is our system. So heat can transfer into the flask from the surroundings and out of the flask to the surroundings, so energy can be exchanged. This is for open and even closed systems. Now, a corked flask of water is considered a closed system. So because water vapor cannot escape or be added to the flask, then no mass can be exchanged for a closed system. Heat can still transfer into the flask or out of the flask from the surroundings, so energy can still be exchanged. Another really important concept I'll say again, so energy, heat is a form of energy. And recall, heat is the transfer of thermal energy between two bodies or two objects that are at different temperatures. So heat is a form of energy. Then in that isolated system, a corked flask of water is considered an isolated system. So because water vapor, which would be the mass exchange, we won't have a mass exchange because we have a stopper that's added to the top of the flask. Then because the system is entirely insulated, then no heat and no energy can transfer into the flask from the surroundings or out of the flask to the surroundings. So open system, both mass exchange and energy exchange. Closed system, just energy exchange. Isolated system, neither mass nor energy exchange. And keep in mind what we've been saying. So these are all the different kinds of systems. The systems will interact with their surroundings depending on what kind of system it is. For instance, in an isolated system, we're not really thinking about how mass and energy are being exchanged with these surroundings because they can't be exchanged with the surroundings. In a closed system, only energy could be exchanged with the surroundings, but no mass. In an open system, both mass and energy could be exchanged from the system to the surroundings and vice versa. Next, two super important definitions you'll see throughout chapter 6. So, an exothermic versus an endothermic process. An exothermic process is any process that gives off heat. So it transfers thermal energy from the system to the surroundings. So notice this wording here, from the system to the surroundings. It gives off heat. We know heat is just a form of energy. So it gives off heat or energy from the system to the surroundings. How you will see this represented in a chemical reaction is if heat is given off in an exothermic process, that means that heat in the form of energy is going to be on the product side of the reaction. So we see energy here on the product side of the reaction for an exothermic process. Then conversely, an endothermic reaction is any process in which heat has to be supplied to the system from the surroundings. Notice this wording again. We need to know what is our system, what is our surroundings. For an endothermic process, heat has to be added for the reaction to take place. So endothermic process, think of this usually as an endothermic reaction or an exothermic reaction. We know heat is a form of energy. So if heat in the form of energy has to be supplied for an endothermic reaction, that means we're going to see energy here on the reactant side of the reaction. Okay, so for an exothermic process or reaction, we are going to release energy in the form of heat. We're going to see that on the product side. Versus an endothermic reaction or an endothermic process, this requires energy in the form of heat. So we'll see energy here on the reactant side of these reactions. Now we'll talk a lot more about this delta H term, which we will think of as enthalpy. Enthalpy can essentially be thought of as also energy. We'll come back to more on enthalpy. This is just to get you started to think about exothermic versus endothermic reactions. We talked about how we either need to input energy or whether energy is released. Remember, for an endothermic process, we need to input energy. So energy is required for an endothermic process to take place and go to completion, versus an exothermic process or reaction is going to release energy at the conclusion of that reaction. So releases energy, heat is given off by the system to the surroundings, whereas for an endothermic reaction, heat is absorbed by the system from the surroundings. Again, we'll talk a lot more about enthalpy. I want to talk about how we start to think about these signs here for enthalpy for an exothermic versus endothermic reaction. Let's start with exothermic. So for an exothermic process, here are our reactants, here are the products. Because these reactants give off energy to the surroundings, that means the products are at a lower energy relative to the reactants. We get an delta H, or the enthalpy of the reaction, the energy of the reaction, as the enthalpy of the products minus the enthalpy of the reactants. The energy of the products is lower for an exothermic process, so we can put in some number like 1 just to see what happens. Then the energy, or the enthalpy for the reactants, is higher, so we'll put in some number like 2. That means for an exothermic reaction, the delta H of the reaction is going to lead to a negative number because the energy of the reactants is higher than the energy of the products. A smaller number here for the products minus a larger number here for the reactants leads to a negative value for the delta H, or enthalpy of the reaction. So the enthalpy, or the energy for the products, is less than the enthalpy or energy for the reactants. Again, because as the reaction takes place for an exothermic reaction, energy is released relative to the starting point of the reactants. We'll do a lot more practice with this. Let me also talk through what this delta H would mean for an endothermic reaction. So we start out with our reactants. We're going to gain energy or absorb energy over the process of the reaction, leaving then the products to have a higher energy or enthalpy than our reactants. So for an endothermic process, the system is going to absorb energy. From the reactants to the products, it absorbed energy. It's at a higher point in energy for the products. Now let's try this. So delta H of reaction is still the enthalpy or energy of our products minus the enthalpy or energy for our reactants. That term does not change. It's products minus reactants. So products minus reactants. Let's see what happens then for an endothermic reaction. We have a higher value for our products, just putting in something arbitrary like 2, and a lower energy for our reactant, so something like 1. That means the delta H, or enthalpy of the reaction for an endothermic process, is going to be a positive value. We're taking a larger number for the energy of the products minus a smaller number for the energy of the reactants. This leads to a positive delta H of reaction. So some important takeaways of exothermic versus endothermic reactions. We'll do a lot more practice with this idea. Next, to set up more of these definitions before we go into some more practice problems. So here, thermodynamics is the scientific study of the interconversion of heat and other kinds of energy. So maybe energy is being created from a reaction. That energy is then outputted in the form of heat. So thermodynamics is of how heat and other kinds of energy are interconverting between one another. Remember, we cannot create nor destroy energy. We cannot create nor destroy energy, so heat in the form of energy or other kinds of energy as well. Remember, heat is just an example or a form of energy. So thermodynamics is how these kinds of energies are interconverting. Because energy can't be created nor destroyed, energy is just interconverted from one kind to another. Next, this concept of a state function. State functions are properties that are determined by the state of the system, regardless of how that condition was achieved. So for state functions, we just ask, what is the final state? We don't care how it got there. We're not concerned with that. Just what is the final state? So some examples of state functions where it only matters what is the final state, not how we got there, not how that state was achieved. We have energy, pressure, volume, temperature as just some examples. For instance, let's say we had some temperature here, that's temperature final. We had some temperature initial here. Let's say that on this object's journey to this temperature final, it kind of decreases for a little bit, then it goes back up, then it kind of levels out, then it goes up very high, then it comes back right here. This whole path that the object took doesn't matter. We only care about that final temperature because temperature is an example of a state function. We can ask, what is the final temperature? What's the final state? It doesn't matter how that final temperature was achieved. So for these state functions like energy, pressure, volume, and temperature, again, it only matters where we end up, not on how we got there. So to calculate a state function like temperature, we're going to take temperature final minus temperature initial. So temperature final might be some point here, maybe that's 100 degrees Celsius. Temperature initial might be 12 degrees Celsius. Again, it doesn't matter that it dropped down below 12 degrees Celsius, then went back up, then leveled off, then went even higher than 100 degrees Celsius. It just matters that the change in temperature is 100 degrees Celsius minus 12 degrees Celsius. So what we're calculating is a final value minus the initial value. This delta, this triangle, means change in. So the change in temperature, because temperature is a state function, we can just ask, what is the final temperature? What is the initial temperature? Again, we're not concerned with how it got to that final temperature or the path it took from its initial temperature to its final temperature, because temperature is an example of a state function. So this holds true for all of these other examples of state functions. This one is energy. The change in energy is equal to the final energy minus the initial energy. It doesn't matter what happened in between. Then this one is pressure. We can calculate a change in pressure as pressure final minus pressure initial. Same for volume. It doesn't matter how it went from the initial temperature to the final temperature. We just take the final minus the initial. That's our change in volume because these are all state functions. So we covered thermodynamics and state functions now. To depict energy as an example of a state function, we can use this visual. Let's say the first hiker takes a route straight up the mountain. So maybe the first hiker is hiker A, whereas the second hiker winds back and forth across the face of the mountain. So they're kind of going like this, then they still end up here. So hiker number 1 and hiker number 2, they still ended up at this point here at the top. Because energy is a state function, we just care about the energy final minus the energy initial. It doesn't matter the route each of them took, they still ended up at that final height, where that final height is related to the potential energy. Right, so the potential energy is only based on the height if we assume they're about the same mass and they're definitely experiencing the same gravitational force. Then because both hikers begin at some initial height, they'll have the same potential energy to begin with. and because then they end up at the same height in the end, they'll have the same potential energy at the end. So even though hiker 1 and hiker 2 took different paths, because energy is a state function, the path does not matter. It just matters where they ended up in the end and where they started with in the beginning. So ultimately, these hikers will have the same potential energy despite the path up the mountain they took. So we've talked about thermodynamics. Now to define the first law of thermodynamics. This is that energy can be converted from one form to another, but it cannot be created nor destroyed. For example, let's say we have the energy of the system and the energy of the surroundings. That equates to 0. Because energy cannot be created nor destroyed, we can just rearrange this equation then and say that for the energy of the system, that's equal to the negative energy of these surroundings. So whatever energy is lost by the surroundings is gained by the system and vice versa. If we know this is an example of an exothermic chemical reaction, where do we put the energy? Is it on the reactant side or the product side? So for an exothermic reaction, we remember that energy is produced, and so energy is a product for an exothermic reaction. So under this idea of the first law of thermodynamics, energy cannot be created nor destroyed. It's just converted between different forms. That means that any chemical energy lost by combustion of this system will equal energy that's gained by the surroundings. So the energy has to go somewhere. Whatever's lost by the system is going to be gained by the surroundings. Whatever is lost by the surroundings would be gained by the system if it were an endothermic reaction. So this holds true for all reactions always. And just as a reminder here, we have the system and then we have the surroundings around it. We picture the system plus the surroundings making up the energy of the universe. Because the energy of the universe is constant, then we just consider these surroundings and the system. So that's how we can make this connection here, is that added detail that the energy of the universe is constant. We're not creating energy, we're not destroying energy, it's just transferring into different forms. So whatever happens in reference to the system is going to impact the surroundings and vice versa. Unless, of course, if it's a completely isolated system. Generally in the lab, it's very hard to achieve a perfectly isolated system. So we're still setting the stage here with these different definitions in chapter 6. So let's go into some additional background on work. So this delta U, remember delta or that triangle is a change in. U is energy or internal energy of the system specifically. You could think of just U as being the energy of the system. Now, I've been saying that heat is a form of energy. Q is how we represent heat. You'll see Q a lot in chapter 6. Q is heat. So Q is the heat exchange between the system and these surroundings. So heat, think Q. Then W stands for the work done on or by the system. Remember, we're always talking about this in reference to the system. We keep in mind that there are surroundings around that system, but with the sign of these values here, we're talking about in reference to the system. So the internal energy of the system is based on the heat and the work. Work then can be equated to the negative pressure times the change in volume. For example, from what we saw in chapter 5, that change in volume, that happens when a gas expands. So based on what we saw in chapter 5, we know when a gas expands, that's going to be an increase in the volume of that gas. So again, these are some equations to be aware of, especially this term of Q, that means heat. And the other big concept here is that we're always talking about this in reference to the system. So the energy of the system is based on the heat and the work. Work relates to the pressure and the change in volume. Sometimes there's not a change in volume. So if this whole term is just 0, then work is equal to negative pressure times a change in volume. But let's say the volume doesn't change. That would just be times 0. Work then would just be equal to 0. So in the cases where there is no change in volume, then the internal energy of the system would just be equated to the heat. That's only, again, if there is no change in volume. A big important takeaway from this slide, though, so let's go into table 6.1, sign conventions for work and heat. Always in reference, again, to the system. If work is done by the system on the surroundings, the system itself is going to lose energy. When it loses energy, it's going to have a negative sign for energy. Then if work is done on the system, it's going to gain energy. So that sign is positive. Again, this is all in reference to the system. We know the surroundings surround the system, but these signs are convention for the system. Next, if heat, which is a form of energy we know, is absorbed by the system, this is also what's known as an endothermic process. If heat is absorbed by the system, we are gaining heat, which means we're gaining energy, which means the system then will have a positive sign for energy absorbed by the system or heat absorbed by the system. We can somewhat use heat and energy interchangeably here. Remember, though, energy is the broader umbrella term, and heat is a form of energy. Then if heat is being absorbed by the surroundings, remember we're always talking about in reference to the system, that means the system itself is losing energy. If the system is losing energy or heat, this is also what's known as an exothermic process. That means the sign for the system is going to be negative. Just to bring us back here again, remember for an exothermic process, that means that energy is being released from the system to the surroundings. That means that this is the system itself, and energy is a product of the reaction. Whereas for an endothermic process, we have to have some input or some absorption of energy. So energy here is on the reactant side for an endothermic process. So for an endothermic process, the system is gaining energy, right? It's absorbing energy. But for an exothermic process, the reaction or the system is losing energy. So then this sign is negative. Let's continue on now. So now work done on the system. You don't need to worry about this specific equation here, but work is not a state function. That's one important takeaway. What's also important then, if work is not a state function, why? What does that mean for something to be a state function or not to be a state function? We saw for that hiker that the route didn't matter for energy, right? So they ended up at the same point. So potential energy was the same despite the route they took to the top of the mountain. That's because energy itself is a state function. If work is not a state function, that means that the route does matter. It means that it matters how we went from some initial point of work to some final point of work. The route does matter for work because work is not a state function. That means we cannot calculate work as just work final minus work initial. We have to know how it got to work final from some starting point. So the key takeaway here is that work is not a state function. Then to be clear about what it means for something like energy to be a state function, and then for work to not be a state function. And again, for work done on the system, it means the system itself is going to gain energy, right? So it's gaining energy. It's a positive sign here. So continuing here for work done on the system, if the pressure of the container remains constant, but the volume increases, then work must have been done on the system. So if we're not changing this pressure that's being pushed down here on this stopper here, but if the volume itself is increasing, however much this volume is increasing, that is proportional to how much work is being done on the system. If the volume increases by a lot, then a lot of work is being done on the system. If the volume increases just hardly or just barely, then not as much work is being done on the system. So we've gone through these concepts with work and a change in volume, but let's actually apply those equations to this example 6.1. So a certain gas expands in volume from 2.0 liters to 6.0 liters at constant temperature. Calculate the work done by the gas if it expands, first against a vacuum and then against constant pressure of 1.2 atmospheres. From the information in the problem, I would start to look at this and say it goes from 2.0 liters to 6.0 liters. That means that it starts at 2.0 liters, then it ends up at 6.0 liters. So volume initial and volume final, we can assign so far. I also like to know what is my system. It's the gas we're dealing with, and then our surroundings are around it. So it starts at 2.0 liters of volume, then goes to 6.0 liters. Let's first do A and then B. So we can draw a sketch like this. We know it goes from 2.0 liters to 6.0 liters. We're first going to think about it being against a vacuum and then against a constant pressure of 1.2 atmospheres. This is also given to us that we're at a temperature that is constant. So we assign the initial and final volumes. Then the work done in gas expansion is equal to the product of the external opposing pressure and the change in volume. So work is proportional to the pressure and the change in volume. So let's see how we apply this to our practice problem. Then what is the conversion factor between liters, atmospheres, and joules? So we'll answer this as well. So we assign the final and initial volumes. What about the pressures? Well, for a vacuum, the external pressure, in a perfect vacuum, I should say, that external pressure is 0 atmospheres. Then the external pressure here in B is 1.2 atmospheres. So with this notion that work is equal to the negative pressure times the change in volume, well, that pressure we're told is in a vacuum. That pressure then is 0. So even with this change in volume, and change in volume is always final minus initial, any change in now we know is the final minus the initial. So final volume minus initial volume. Because we're going against a vacuum, that pressure is 0. We plug in 0 for the pressure. That means that the work done in the expansion is 0. So technically 0 work is done when we're working in a vacuum where there is 0 pressure. So 0 external pressure for a vacuum. Then for B, this pressure is 1.2 atmospheres. So let's plug in 1.2 atmospheres to our work equation here. So work is equal to negative P. We plug in 1.2 atmospheres. Change in volume, again, is volume final minus volume initial. We know that it started at 2.0 liters. Then we're told it ends up at 6.0 liters. So that change in volume term is 4.0 liters. Multiply that by 1.2 atmospheres. Keep that negative sign out front. So the work done here, negative 4.8. Then the unit is liters from that change in volume and atmospheres from the pressure. So this work here, we have atmospheres and we have volume, so in liters. It comes out to be negative because the final volume is greater than the initial volume. So this is a positive term. The pressure is positive, it's always positive. But that negative sign out front then makes the work a negative sign. Let's think about that for a second. What does it mean for this to be a negative sign? Well, we're always thinking about in reference to the system, right? So if there's a negative sign for the work in reference to the system, that means the system is doing work on the surroundings, right? So it's losing some of that work. It's losing some of that energy. So the system is losing energy because it's doing work to the surroundings. The system is doing work, it's losing energy, so it's going to have a negative sign. So the system is doing work on its surroundings, and that negative sign then makes sense, especially because we're going from a smaller volume to a larger volume. So it's expanding in volume, it's doing work on its surroundings. It's going to have a negative sign then for work. So we solve for work in liters atmospheres. We can do a conversion into joules, and joules is our term, our unit for energy. So for energy, we're usually seeing this in joules. We denote joules as capital J. So one conversion factor that may be helpful is going between liters atmospheres and into joules. This conversion factor is 101.3 joules per liter atmosphere, or 1 liter atmosphere per 101.3 joules. So with this conversion factor and then having our units of liters atmospheres in the numerator here, we need to orient the conversion factor like this. So we multiply this by 101.3 joules per liter atmosphere. Liters and atmospheres get canceled. We leave that negative sign out front. The work then in joules is negative 4.9 times 10 to the 2 joules. Just to reiterate here, this umbrella term for energy. So under this umbrella term of energy, heat is a form of energy and work is also a form of energy. So I wanted to clarify that here. So we're calculating the work. We're also calculating energy then, because work is a form of energy. So here, work in liters and atmospheres, we convert that into joules using this conversion factor. So we get that as our final answer. You should just have 2 sig figs here. If we are going to visualize this number out of scientific notation, so negative 4.9 times 10 to the 2. As a review here, we're going to go over 1, 2 decimal places, so negative 490 joules. And this is after we rounded to 2 sig figs. So for an important check, because the gas is expanding, work is done by the system on its surroundings. That means the work done has to be a negative sign, and it is, so this checks out. Let's try this one together. So example 6.2 in your textbook and in the main slide deck. So the work done when a gas is compressed now in a cylinder is 462 joules. During this process, there is a heat transfer of 128 joules from the gas to its surroundings. We're going to calculate the energy change for this whole process. Recall that energy is a state function. So just a reminder here, energy is a state function. So we would take energy final minus energy initial to find the change in energy, or also represented as that change in U, so the change in internal energy. So if compression is work done on the gas, so work is being done on the gas, that means that in reference to the system or the gas itself, we're going to have a positive sign for work. Work is done on the gas from the surroundings, so again, we're increasing the energy of the gas here, or the system. It's going to have a positive sign. If the system were doing work, that's when we have a negative sign. Now though, work is done on the gas, so we're going to have a positive sign. Heat is released by the gas to the surroundings. Heat we know as Q. We're going to think about, is this an endothermic or exothermic process? If it's exothermic, energy is released as a product. We can think of that as, if it's endothermic, then energy is absorbed. And we think about energy being on the reactant side. Then we'll think about what is the sign for Q. We now associate Q with heat. Going back to the setup of the problem, we have the work done here, work done on the system or on the gas. That's going to be a positive value, and we're told it's 462 joules. In this portion here, we're told there's a heat transfer. So heat represented by Q of 128 joules from the gas to the surroundings. From the gas to the surroundings, the gas is transferring heat. The gas is transferring heat. That means the gas is losing heat. The gas is losing heat to the surroundings. It's transferring heat to the surroundings. If gas is losing heat, and heat is a form of energy, if the gas is losing energy to the surroundings, that means that the gas is undergoing some exothermic reaction. So the gas is losing heat over time, over the reaction. If energy is being released by the gas or being transferred by the gas, which is our system, energy is being released by the system. That is an exothermic reaction. Then if heat is being transferred, and we always think about it being in reference to the system, if the gas or the system is losing heat, that means the sign here, again, always in reference to the system. The gas is losing heat, the system is losing heat. That's a negative 128 joules. So a negative sign here for heat. So work, a positive sign, again, in reference to the system. Heat, a negative sign in reference to the system. So we practice using this equation. Now for this practice problem, we need to use this equation. The internal energy of the system, which in our case, we're looking at that gas, is based on the heat plus the work. The signs here are extremely important, right? Because if it was a negative versus a positive sign for work or heat, that's definitely going to impact the value we get for the energy of the system. So the change in the energy of the system is Q plus W. For the Q term, the heat term, we know that the system is losing heat to the surroundings, so that negative 128 joules we plug in for Q. Then the work term, we go back up to the setup of the problem. The work term, work is being done on the system, so work is positive, so positive 462 joules. Work is done on the system because we're compressing the gas that is our system. The gas isn't expanding, the gas isn't doing work. Work is being done on the gas as it's being compressed. So then a positive sign here for W, positive sign here for work, then negative 128 joules. Again, signs are extremely important. Positive 462 joules totals up to 334 joules for the change in energy of the system. So even though heat is being released by the system, work is being done on the system. Overall, we end up with a positive value because the work being done on the system is greater than the heat being released by the system. That means the energy of the gas increases altogether by a positive 334 joules. So as we're at the end of part 1 here in chapter 6, be sure you're really comfortable with this table here, these different sign conventions, again, in reference to the system. Let me know if you have any questions about anything. I will talk to you very soon for more on chapter 6.